I'm Annalisa Russo,
And I'm Michael Bell.
and today we're going to show you how to make a paper Arduino, or a paper Duino, using the circuit scribe and a pen plotter.
Our paper Arduino is based on the Arduino Pro Mini. We took the schematics and Eagle files from the Arduino website. We modified the schematics found so that they would work in a pen plotter. You'll notice that we changed very little. The through-hole connectors are changed to pads that are printed. A few buttons are also changed, and a few surface mount components are made larger for ease of placement.
Now let's switch on over to the board layout. We arranged the components and traces so the board can be printed in a single layer. For example, you can see here that we use the reset button itself as a jumper. We also set the line width to 0.6 millimeters to match the width of the pen traces. The minimum distance between lines in this particular pattern is 0.1 millimeters. Since the pen plotter only prints lines but not fill patterns, we designed our large pads out of concentric circles and then also built up the pads for the components with some extra line features like this. Here's the power circuitry. When designing the layout, it's important to put chips close together to minimize the line resistance between them, but not so close that it's difficult to place the components. We're using components with the 1206 package, which is a bit larger than the original components from the Arduino. So we didn't quite get all the traces into a single layer, but we left room for a jumper sticker just in case we ever want to use digital pins 1, 2, or 3. Remember, you are limited to a 4x3 inch working area in the free version of Eagle. Before we export the layout, we need to deselect every layer in the file except the top layer of traces. Then we'll export the layout in a DXF format and deselect both the wire width and the fill area options, and then save the file. Finally, make sure you measure the size of your board layout before moving on to the next step.
Once you export the DXF from Eagle, you can drag it into a new sheet in Silhouette Studio. You'll notice that our scaling is off. We need to adjust the vertical height to 2.945 inches. Once adjusted, you can reposition the layout anywhere on the page. You'll notice if you zoom in how the pen plotter actually prints each of the traces and pads. The pads are concentric circles to try and increase the conductivity of them. Other surface mount component pads also have lines going back and forth. All of the lines will be repeated twice. Next, you can go and hit the Send to Silhouette button. We're going to change some settings here. The speed of 1 is best to lay down the most amount of ink. We're also not using a cutting mat, so we can uncheck that button. Our thickness at 15 is perfect for photo paper.
In the meantime, we need to get the plotter ready for printing. First, we'll wrap the pen in masking tape, and then wedge the pen into the plotter head. Finally, we insert glossy photo paper into the plotter. It's a good idea to first print a few test lines to get the height of the pen correct. It should draw straight lines when the plotter head is down, but not drag on the paper when the head is raised.
Once you're ready, click Cut.
You can attach components using a dab of superglue, then placing the chip with tweezers. This method should be sufficient to make contact with the traces, but sometimes we reinforce the connections with conductive epoxy. Or as an alternative, you can apply a piece of Z-axis tape to the pen traces and press the components down.
We used an Atmega 328 that has already been bootloaded. A bootloader can be thought of as an operating system for the microcontroller, and before you can upload an Arduino sketch, you must have a bootloaded chip. A bootloader programmer costs around $20 and can be found on SparkFun and other websites. In addition, a USB to FTDI cable needs to be connected in order to upload a sketch. To make the jump from the FTDI cable to the pads, we use our Arduino connection kit with magnetic connectors. For a simple example, we placed our bidirectional LED component on pins 6 and 7. After programming
My name is Ivan Pubarev, and I work for Advanced Technology and Projects Group at Google. The hand is the ultimate input device. It's extremely precise, it's extremely fast, and it's very natural for us to use it, right? Capturing the possibilities of human hand was one of my passions. How can we take this incredible capability, finesse of human actions, or finesse of using our hand, but apply it to the virtual world? We use radio frequency spectrum, which is radars, to track human hand. The radars has been used for many different things, to track cars, big objects, satellites and planes. We're using them to track micro motions, twitches of human hands, and then use that to interact with the wearables and Internet of Things and other computing devices.
Our team is focused on taking radar hardware and turning it into a gesture sensor. Radar is a technology which transmits a radio wave towards a target, and then the receiver of the radar intercepts the reflected energy from that target. The reason why we're able to interpret so much from this one radar signal is because of the full gesture recognition pipeline that we've built. The various stages of this pipeline are designed to extract specific gesture information from this one radar signal that we receive at a high frame rate.
From these strange foreign range Doppler signals, we're actually interpreting human intent.
Radar has some unique properties when compared to cameras, for example. It has very high positional accuracy, which means that you can sense the tiniest motions.
We arrived at this idea of virtual tools because we recognized that there's certain archetypes of controls, like a volume knob or a physical slider, a volume slider. Imagine a button between your thumb and your index finger, and the button's not there, but pressing this is a very clear action, and there's a natural physical haptic feedback that occurs as you perform that action. The hand can both embody that virtual tool, and it can also be acting on that virtual tool at the same time. So if we can recognize that action, we have an interesting direction for interacting with technology.
So when we started this project, me and my team, we looked at the project idea and we thought, are we going to make it or not? We don't know, but we have to do it. Because unless you do it, you don't know.
And what I think I'm most proud of about our project is we have pushed the processing power of the electronics itself further out to do the sensing part for us.
The radar has properties which no other technology has. It can work through materials, can embed it into the objects. It allows to track really precise motions. And what is most exciting about it is that you can shrink the entire radar and put in a tiny chip. That's what makes this approach so promising. It's extremely reliable. There's nothing to break. There's no moving parts. There's no lenses. There's nothing. It's just a piece of sand on your board.
Now we're at a point where we have the hardware where we can sense these interactions and we can put them to work. We can explore how well they work and how well they might work in products.
Blows your mind usually when you see things people do. And that's what I'm really looking forward to. I'm really looking forward to releasing this to the development community. And I really want them to be excited and motivated to do something cool with it, right?
you